You look just as pretty in Earth light as you do in sunlight. Coming in. There it is. Proceeded. As I step off at the surface at Taurus Littrow, we'd like to dedicate the first step of Apollo 17 to all those who made it possible.
At some point in my life, I will go to space. And I'm confident in that.
I think that we need to work on controlling our resource consumption and what we're using as resources before trying to colonize another planet. We need to sustain what we have here.
In the future, we will need to feed more people. The world population is increasing.
The demand for food will be 70% higher than it is now. Even today, close to 1 billion people go hungry every day.
In the meantime, the resources that we have to produce food is decreasing. Water is becoming more limited. Fertilizers becoming more limited.
However, I think it's really extremely important that we push the boundaries because once we do that, we open possibility that we cannot predict at this point.
There are interesting things that can be learned from the space research efforts.
The lunar greenhouse and its closed system is very unique. There's only 1 or 2 universities in the world that are continuing to work on this project.
The lunar greenhouse system is an automated machine, mainly providing food, oxygen, and water for astronauts.
The concepts that are built into that, the biology and the engineering, all of that is being employed here on Earth today to demonstrate how we can solve these problems.
Especially toward the beginning of the last century, the early part of the 1900s, people were really so worried about Malthus's prediction that population will overrun food production and that people would go hungry. And in a way, it's not really completely unjustified because there are certain countries that really suffered from famine. And of course, in the 1950s, especially the 1960s and part of the 1970s, we had the Green Revolution, where scientists were able to select for high-yielding varieties of cereals and other crops. But of course, the Green Revolution has solved certain problems and addressed certain challenges, but then it also created new challenges. And I would say that the main challenge that it created is the issue of sustainability. With increasing global population, which is accompanied by new technologies. And so, of course, there's more people to feed, and globalization has also contributed to this because it's lifted millions of people out of poverty, particularly in China and India and other emerging economies. And so now people have purchasing power. And those people with purchasing power would demand better quality food and at the same time more food. And so with all of this taken into consideration, I think it's not unreasonable that the prediction is that we're going to need 70% more food in the middle of the century than what we have today. Accompanying the trend of the rise in global population is that trend of urbanization worldwide. So today, for instance, there are many countries now with multiple cities with more than 1 million people each. China today, for instance, has over 100 such cities. And the prediction is that by 2030, China will have over 220 cities with more than 1 million people each. We're faced with a world that is confronted with that issue of sustainability. So how do we then produce enough food, again, for the rising population worldwide in a way that would minimize waste, in a way that would minimize the inputs into it, and that would minimize its dependence on the external environment. I really believe that the space agencies can serve as catalysts in terms of really accelerating the development, the design, not in outer space, but on Earth.
We need very reliable and sustainable systems to keep the space explorers alive. And I think there's an interesting parallel here with now living on Earth. We need to think about sustainable living on Earth as well. We want very efficient electric lighting to grow the plants. We want to recycle all of our water and all of our nutrients as much as possible. So we want to close these loops to be very efficient. And so as you go farther and stay longer, now you need these regenerative capabilities, and they need to be sustainable. The external space environment's very harsh for living organisms for a number of reasons. There's no atmospheric pressure, so anything that has water in it would boil away very quickly. It has extreme temperatures. If you're exposed to sunlight, it can be very hot. If you're shaded, it can be very cold. And as part of that sunlight, you're getting all the UV radiation that comes from the sun. And so you can envision coming up with basic ideas, testing them out, building prototypes, maybe then testing them in relevant environments, and then having an actual functioning system, maybe in space.
Lockheed Martin did a study, and they identified South Pole Station as the best analog for Moon and Mars. Their record low is 118 below zero Fahrenheit without the wind chill. It's the actual temperature. It was minus 50 or something every time I was out there. But at those temperatures, once you get down below minus 50 or whatever, it's all the same. It's flat white in 360 degrees. There's, you know, the highest point you can see is maybe a foot tall snowdrift. You know, so it's barren. And it's extremely dry. It's the driest place on Earth. You know, it's a desert. It was a great time. I spent 13 seasons down there, 13 summers. It's weird when you don't see a plant for 6 months. You don't see an insect for 6 months. You know, it's strange. I had the director, Dr. Peter Wilkness, and the director of the NSF brought a bunch of senators down. And I'd been trying for a couple of years to get a greenhouse program started. And anyway, I met the director, and I caught him in the bar that night with a white paper and said, "This is what I'd like to do." And he put his arm around me and said, "This is a great idea, let's do it." You know?
It's using conventional technologies, things like sodium lamps, but it's being done in a very relevant environment, so it's isolated, you know, hostile external environment. So that's an important step along the technology readiness level. But that might not be exactly what you envision, say, for a large-scale lunar greenhouse. And so a parallel technology development might be an inflatable, deployable structure, like the lunar greenhouse effort at the University of Arizona.
I worked many years as a researcher to get the background so that I could help direct a program. There's a lot of satisfaction in organizing groups to reach an end goal. There's a lot of satisfaction there. All we're doing is mimicking what the plant would expect to have if it was on Earth, and taking its byproducts without even telling it, kind of like we do on Earth, and make use of it for life support. The day begins for the plants in the lunar greenhouse by providing energy from the lamps. Just as the sun provides it to the earth after sunrise, the environment begins to change, the plant responds, it begins growing, and the day has begun. It's all linked to solar radiation. It's the sun's energy that the plants capture and make biomass. They grow. In that process of growing, the photosynthesis, they absorb carbon dioxide from the atmosphere and give back oxygen. And we as humans are greatly dependent on the plants. The humans could go away and the plants could survive. But I'm not so sure the other way around. It's us providing them the carbon dioxide, and particularly in the lunar greenhouse, and it's the plants providing back the oxygen. The entire system of the lunar greenhouse does represent, in a small way, the biological systems that are here on Earth.
So there are two basic cycles that we're looking at in the lunar greenhouse, our water cycle and our atmospheric cycle.
You start with the astronauts, put out carbon dioxide. You introduce it into the greenhouse and the plants convert it to oxygen.
The water cycle begins with fresh water that we either bring with us or discover where we are. From there, that water is then oxygenated and given nutrient salts. That water is then continuously flowing across the root zone of the plants and returned to the system.
We can run it in the makeup water for the plants, which transpire it into the atmosphere of the greenhouse, and then we condense that atmosphere and we get clean water. The crew uses this water for hygiene water, for drinking, and this water, this wastewater is generated, which goes into the composter, and you harvest this gray water from the composter's atmosphere. Roughly a person's weight in hydroponic salts can keep one person alive for a year.
As a kid, as 6, 7, 8 years old, designing on a piece of paper with some pencil or pen or colors, that developed passion for space. I'm part of the OSIRIS-REx asteroid sample return mission team. My role is I'm the ground segment systems engineer. Power and mass are two important factors in designing space systems. And generally speaking, we would like to have more and more power. But nevertheless, generally power means, or power availability means, is translated in weights, which then is translated in cost. The lunar greenhouse, I'm responsible for the solar concentrator power system. Our approach aims at integrating the power of harnessing solar radiation and splitting the spectrum in two portions and use it as much as possible for free.
Many people have talked about burying structures on surface missions, like going to the moon or to Mars. One of the approaches that's been around for a number of years now is called the Himawari system. And this uses Fresnel lenses that you can put it on a tracking drive and it will then track the sun and collect and concentrate the light so you can deliver it to the plants.
Not only can you get the visible light, but you can collect the non-visible light, the UV and the red and far red, and you can use that too, so you can harness the whole spectrum.
This is where all the light from the Himawari comes in. And as you can see, each one of these is transmitting the sunlight that each of the lenses collects. Ideally, you would have two curves, one for the inside par and one for the outside par. As you can see, we've got kind of the dip. That's the big thing we're trying to figure out now, what's causing that, what we call the midday dip in the inside par. Trying to work through that and figure out what's going on.
We'll harvest the plants. You got the 4 quadrants, 6 plants in each. Transplant these as normal. But what we'll do is what we talked about before. We're going off this routine as of today. All right, let's start harvesting.
So every week we get the biomass, we put them in these bags. Erica measures them.
They don't take a whole lot of work to pollinate. What we do when we come in here is we just make sure to brush our hands over the flowers and the bushes. And usually that's enough to get kind of pollen spread around and get the flowers fertilized. It's cool, it's humid, it's so much different from being outside where the air is just so dry.
Because plants are soothing, they are psychologically beneficial to the people working under these extreme environments. That's been demonstrated at the South Pole. NASA has demonstrated it on the space station.
But I don't think the astronauts are the ones that are going to be running the greenhouse. I think it's going to be have it automated as much as possible.
Going beyond the visible range and going inside the plant with the advanced technology, sensing technology, that gives us the power and the tools to better manage that crop and greenhouse system in terms of resource use. So basically the system actually creates a color-coded graphics indicating the stress zone with red color, for example, and indicating the well-watered or non-stress condition with green color before those symptoms and stresses are visible to human eye.
So 9 a.m. on Mars is probably next week. Right. Yeah, I got a meeting next week because that's the only time our time zone's match.
South Pole, this is Michael.
Hey, Mike.
How are you today? How's the weather down there?
Well, it's wind chill brings it down to negative 72.1 degrees Celsius.
Lane Patterson has gone down. He was our student through the construction of it, and you know, he's done his thesis on the South Pole greenhouse.
So Lane, what we're going to do is we're going to go through what it would be like if we're calling you from the moon and you are on Earth.
Okay, Mike, this is South Pole calling you at the moon. I'm looking at the Lunar Greenhouse Situation Report, and I'm seeing that our oxygen production is a little low. How are you guys breathing up there?
It's a little tricky.
Lane?
Yeah?
Lane, there was a big harvest.
All right.
There was a big harvest, more than we thought, so we might have dropped down a little bit. You think we're going to be able to recover okay?
So, using the Rensis platform, our operator connecting from South Pole Station was able to access the real-time data and be able to monitor the key variables and all those resource balances and also the alarms generated from the lunar greenhouse system. And he was able to provide directions or suggestions for better management of the lunar greenhouse system.
One of my goals would be to have a constant supply of oxygen coming out of this unit, even though we're harvesting a little bit every day.
The thing that would excite me the most as a researcher is to see the real functioning biological life support system doing what it's supposed to do. And so I think it's an interesting thing to consider that we're taking our sort of terrestrial companions with us because we need them. We're intricately dependent on them.
We have a lot of problems on Earth, big problems that we need to solve. Although historically I do believe that we have come a long way over the past few centuries in solving problems. I don't believe that it works just by focusing on one problem at a time, try to solve and then move to the next. Space exploration helps us to explore, to push the boundaries of what we know and opening opportunities.
What we learn from this controlled environment system will and already is being applied here on Earth and to produce great food in urban areas or in areas that are not normally thought of as food production areas.
There are some case studies that really are quite fascinating and captivating, and that is in the Middle East. You'll see these modern cities that are rising from the sands. And because of the food crisis that took place in 2008, 2009, a lot of these countries, which are quite rich, were awakened to the fact that despite their riches, they may not have access to the food that they need. And so this really taught them a lesson that they need to try their best to be able to produce as much food as they could locally. I've had the privilege to design an integrated farming system or food production system where we directly apply this thinking and philosophy of an integrated system where the waste output is minimized and all the resource inputs as well are minimized. Mega cities that are being created in places like China and India, where this thinking, this philosophy, this technology of an integrated system where the resources are continuously and constantly recycled. Whatever is the waste output from one unit within the system will have to be used as an input into another unit within that system. And it would be in such a way that its food production component is totally self-reliant. This is where that concept of viewing cities more like as a space colony, as a moon base, for instance, could be quite useful.
In the highly populated regions of the world, it's even more important that recycling is done and resources are used more efficiently. And there may never be an opportunity to go to the traditional outdoor farms. The land may not even be available, or the quality land so that you could farm. And maybe most importantly, guaranteeing quality and safety of the food. And many people are thinking about this now, not just engineers, but young people that are dreaming about how they're gonna survive in the future.
In 2050, I will be 66 years old.
I'll be 58.
I will be 60 in December of 2050.
Pollution, food, fresh water, the pressure on those things can be alleviated by integrating agriculture into urban centers.
Man hasn't really given me a pessimistic view enough to say, hey, we're going to be gone, and in 200 years, the ants will roam and rule the earth. And I think we're too arrogant to actually let that happen. However, the damage that we cause in the process is the measure of our success.
One of the ways of the young people reconnecting right now, where they could not in my generation, now urban agriculture. People that you would never think are even interested are getting into it. So it's becoming more prevalent because of controlled environments and hydroponics, making a better connection, I think, because it's bringing it back to the urban regions.